Hi, my name is Sarah Jakes, and my presentation's on the RSA algorithm in cryptography. The three main points I'm going to talk about are why the RSA algorithm came about, how it works, and I have some programs that I made to show you, and the connection to secondary education. So before the RSA algorithm was developed, there was this problem of key distribution, meaning like in order to encrypt or decrypt a message to send to a person, or if I'm receiving one, we would first need to share the encryption or decryption key. And so in order to share a secret message, we needed to first share a secret key, which is kind of a catch-22. So some solutions to this problem were exchanging the key face to face. So if I wanted to give somebody in California my secret key, I would fly out to California and meet with them in person. It's obviously not very efficient or cost-effective method. So another option is to have a third party deliver the key. But this definitely should be somebody you trust because if they wanted to, they could decrypt your message and give it to your key to whoever they want, and you wouldn't even necessarily know. Or the third option would be through an encrypted channel, but then you're back at the beginning because in order to send a message over an encrypted channel, you need to exchange the encryption key first, and it's just kind of a cycle. So this had been a problem for a while throughout the history of cryptography, but especially, um, with computers coming about, William Diffie in the 60s saw this becoming an even greater problem once computers were more widespread. So, Diffie published an idea of an asymmetric cipher in 1975. Up until this point, all the ciphers had been symmetric, meaning the encryption key and decryption key were identical. He had this idea of an asymmetric cipher, meaning you could have this public key that you could give to whoever, and then you'd have a private key that you keep to yourself to decrypt the message, and that would kind of solve the issue of the key distribution problem. He just had this idea, though. He didn't actually know what method would actually be used to go about doing it. So in 1977, Rivest, Shamir, and Adelman found the solution, which is the RSA algorithm, which is named after the first initial of each of their last names. But what I found was interesting is actually Clifford Cox solved the problem first, but did not receive credit until 1997. He worked for the government communication headquarters in the UK, but his work was classified. So even though he solved the problem, I think 4 years before um, Rivas, Shamir, and Adelman, he didn't receive credit until his work was declassified in 1997. So the way the scheme works is basically, like I said, you have a public key, which would be the numbers E and N that you give to anyone you could publish online, whoever wants to send you a message. Then you have a private key, which would be the number D and the primes P and Q, which you would keep a secret. Anyone who could factor N, which is the product of P and Q, could then find D and decode your message. So with computers getting faster and faster, we make the primes P and Q bigger and bigger to make it harder to factor N. Right now, I think P and Q are 150 digits long each. So I want to give you an example of what encrypting a message would be like. So first of all, you need to change the letters to numbers. And in my case, I'm just going to have A equal 1, B equal 2, and so on. But if you were actually going to do this, you would probably use the ASCII 2, um, which converts each letter to binary to encrypt. But for this situation. I'm just gonna do it this way. So I want to encrypt hello, and so you can see there's my message changed to numbers. N is 1189 and E is 611. And these are the two things, the public key that I would just find online. And then, so to change 8 to the encrypted text, I would just take 8 to the 611th power mod 1189. And then I do that with 5, 12, and so on. Okay, so I'm going to show you the program I made that does this. And it basically does just like I told you. It takes each number in the message to the power of the encryption key mod n, which in this case is 1189. So enter in the message, and there is my ciphertext, or the encrypted message. Okay. So now I'm wondering to myself, how safe is this message if I were to send it to somebody? So, or send it to the person. What if it's intercepted? Basically, like I said, that's based off of how hard or easy it is to factor the value of n. So I was doubtful of how hard or long factoring actually takes. Even if n is really big, I'm thinking to myself, it can't actually take that long to factor it. So I wrote a program that makes a list of the prime numbers and then checks n to determine which primes it is divisible by. So first let's check the value of 1189. So make a list of the first 20 prime numbers, factor 1189. That went in the blink of an eye. So my message to whomever I'm sending it probably isn't that safe. But let's say n is 63,083. For 1189, that's a 2-digit times a 2-digit. For this one, I took a 3-digit times a 3-digit. And you can already see just by that small change how much longer it's taking to factor n. So this helped convince me a little bit that, okay, maybe factoring isn't as easy or as quick as I thought. I believe this ended up taking about 2 minutes to factor. So to decrypt a message, then I'm going to walk you a little bit more through this step by step. To decrypt a message, I would know what the two primes P and Q were. They should be random and large. And then I would have made the encryption key, which is E, an odd number that should be relatively prime to P minus 1, Q minus 1. And then I would need the message that I wanted to decrypt. My output would be the decrypted message, and also just for fun I had it output the decryption key, even though really you wouldn't need to have that outputted. So the steps my program does is it calculates P times Q, which is n. It calculates P minus 1 times Q minus 1. And then the extended Euclidean algorithm could be used to find D, which, to remind you from what we went over in class, the extended Euclidean algorithm writes the GCD of two numbers a and b as ax plus by, for where x and y would be integers. So in our case, the GCD would be 1 because e and p minus 1 times q minus 1 are relatively prime. And then we would try and find the integers x and y, where x would be the decryption key in our case. But to be honest, I wasn't quite sure how to get my program to do this. So I had it calculate 1 equals e times x mod p minus 1 times q minus 1, and basically had to increase x until we got a true statement. And so then to decrypt my message, I would just have to take the message to the x power mod n. So this is the message I received. Here's P and Q and E. I would find D by taking 611 times D mod 28 times 40, which is P minus 1, Q minus 1. And I just increase D until I get a true statement, which is 11. And then I would just take the first number in my message to the 11th power mod 1189. And after I've done that with my whole message, I just compare it with what value each letter represents. So so if we want it 29, 41, 611, enter in the encrypted message. This could also be called the cipher text. Okay, and then it outputs exactly what the original message was and the decryption key. So some connections to the secondary classroom. One thing is this discovery in cryptography was relatively recent. I mean, to the students, I guess the 70s might seem like ages ago, but I feel like in the math sense, as far as discoveries goes, this is pretty recent. And so I just think it would just be good to talk about that fact, and then the fact that there are still problems that haven't been solved in math. Not every problem has already like been given a solution. So in cryptography, the saying, if it's not broke, don't fix it, doesn't really apply, because you want to stay ahead of the cryptanalysts. So people are trying to find ways to break the RSA scheme. So are there faster methods to factor? If they are, I would want to find them first before somebody else finds them, or prove that there aren't any. Confirm whether modular root extraction is as hard as integer factorization. Find alternative methods of public key crypto systems. Right now, it's just the RSA scheme. So what other hard problems are there in math that could be used to create new crypto systems? So actually, the Iowa Core has a standard in the numbers and quantities domain that talks about information processing in the internet. And specifically, the number 6 one talks about basic number theory, modular arithmetic that's used for the public key cryptography. So there's a great applet I found online. That relates modular arithmetic to clocks. And I feel like maybe I've heard about that before, like calling modular arithmetic clock arithmetic, but to be honest, had forgotten about it, I guess, until this point. So why not really modular arithmetic to something the students use every day? Like if it's 9 o'clock, what time is it going to be 5 hours from now? It's not 14 o'clock, it's 2 o'clock. The student just did 9 plus 5 mod 12. So this allows you to input a starting time